So we're now being recorded.
Yes, I forgot at the beginning.
Okay. So something happened. Hold on.
So share the screen.
Share the screen. Yeah, I have to get back to the
Glasses over.
get my glasses. Forgive the interruption. Something with the recording screwed up the Zoom, so I lost the Zoom for a second. Oh, here we go.
No, this is my one. You have to share your screen. You do have to share, but because I have not in your.
Right, I know. But I might have, what, am I still a participant? I think I'm not a participant. Oh, you know what I did? I didn't join the meeting. I left the meeting because it said, are you bothered by the meeting recording? So I left the meeting. So give me a minute while I get back on the meeting. This is an intermission, a very early intermission. My apologies.
Do you join the meeting?
Have to join the meeting.
But Marco was checking the chat.
X5, 4, 7, 6.
Marco.
Yes.
Yes.
Okay, I'm back.
Okay, now you can share. Marco. You have to open.
Oh, it's right here. Yeah.
Okay.
All right, we're back. My apologies for that delay. For that, because technical difficulties. Does he have a question, Rafi?
No, now I think everything's all right. Cameron told him what to do.
Okay.
Okay,
Okay.
just close this.
Okay, good. Go.
Okay. So the as I said in the beginning, or when I was
And outside that he cannot hear now.
He could not, but now he can he?
Somebody
Marco is
give him a message.
No.
Can you?
I couldn't hear.
Yeah, it's just comments. It's just comments. Stop.
Can you explain the pigeonhole again?
Can I explain it again?
Yes,
Okay, so the pigeonhole, oh, that's what he missed on the board.
exactly.
Okay, so it's just, suppose you have a container with 10 slots and you have 12 pigeons to put them in. Then we all know that there'll be at least one slot with more than one pigeon. So the general pigeonhole principle is that if you have n slots and n things to put in them, you're going to have at least one slot with more than one thing in it,
If m is greater than n.
if n is greater than n. That good, Rafael?
Okay.
All right, so yeah, so the Benasser at the end of this famous paper, what numbers cannot be, presents or sketches at least a formalist position, and that's what's behind, or that's what gives a philosophical perspective to this formal theory I'm presenting. But the paper itself isn't known for what he's saying at the end. So what he says at the end is what I know I do when I write papers, when you said what you said you're going to say, and then you can like kind of speculate freely. And then no one expects as much out of it. So he gives these ideas. So what he's known for, though, what he did in the paper is defend this claim in a very compelling way. It's a classic. This claim here that words like 3 and 17 they're meaningful only with respect to an antecedently understood natural number structure. So the point is 3 doesn't refer to something on its own. It has the natural number structure behind it with which we understand the number. So that's what the paper is known for. But at the end of the paper, he sketches this formalist position. So I'm going to read the relevant quotes where he does this. Okay, so can skip the slide here. Oh, well, never mind. There are not two kinds of things, numbers and number words, but just only one, the words themselves. Most languages contain such a sequence, and any such sequence of words or terms will serve the purposes for which we have ours, provided it is recursive in the relevant respect. In counting, we do not correlate sets with initial segments of the numbers as extra linguistic entities, but correlate sets with initial segments of the sequence of number words. The central idea of this formalism that he's sketching at the end is that this recursive sequence is a sort of yardstick with which we use to measure sets. So questions of identification of the reference of number words should be dismissed as misguided in just the way that a question about the reference of the part of a ruler would be seen as misguided. Okay, so I think to get at what he's trying to say here, it's helpful to talk about his distinction that he makes early in the paper between intransitive and transitive counting, which Marco was asking about earlier. So it's a pretty simple distinction. What he calls intransitive counting is just reciting the number words. So here's an example of intransitive counting. 1, 2, 3, 4, 6, 7. Okay, you just saying the number words without relating them to anything. Transitive counting, so the point of the terminology, it's like a transitive verb now. Count is now a transitive verb. It has something as its object. That process is directed at something. So we had an example, I gave you an example earlier. When you transitive count, you're using this number sequence to give you an answer to a how many question. Okay, so the example I gave in the first few slides is just an example of transitive counting. So I take there to be two really main points that Nasraf is saying at the end of the paper. That this is something throughout the paper. When he first introduces the transitive and intransitive counting distinction, he observes that intransitive counting is prior in a certain sense. We need to be able to count intransitively before we could ever count transitively. But then also, and this is where his formalism comes in, when we count intransitively, it's a facility with a formalism, the number system of the language. It's our ability to know what the next number is after we set a number, but also given two numbers to know which one's greater than the other. We just know that right away. But it's a formal fact. It has to do with the language system or the number system of the language.
Sorry, there is one point here, so I don't know whether we can discuss it now or later. The idea of transitive counting, as Bernard presents it, is an association of words and objects. One with this object, two with this object, three with this object. Okay. But in fact, the same operation can be done by associating any domain of object to any domain of object. So you can this to this, this to this, this to this. So for example, instead of 1 to 3, you can associate a bar, a strokes, this, a second stroke to this, a third stroke to this. And this is essentially the same things. But the point is that when you have associated strokes rather than words, and you arrive in the end, what we have in the end is a strokes. It's not 8. So now we have to count the strokes to see that you have 8. So in some sense, it seems to say that this intransitive counting is not simply the operation, the transitive counting is not simply the operation of associating, but the operation of associating with a structure that has an intrinsic order that is given by the name that we use.
Yeah, I think so.
Okay.
Right. I mean, I think that's part of his point, is because we're using it to answer the question of how many there are. And what you described, the exercise of associating strokes with something, doesn't answer that question. But the number word system does answer the question.
So in some sense, the system of number words is a sort of good, perfect progression, is the good model of the numbers in some sense, the model of reference.
He calls it a ruler, right? It's not, I don't know, it's effective, it's a practical point.
Okay,
Right?
okay.
It's a linguistic technology.
Okay.
That's the way I would put it.
Okay.
Okay. But yeah, this linguistic technology is purely a formalism. It's words with certain relationships. 7 as a a sound, as a phoneme, it doesn't, has to be exist within formalism to have this property. So it's also, yeah, he's not talking about the number word in itself. He's talking about the number word within a linguistic system where you have this ordering, this idea of the next element.
John, can I ask a quick question?
Okay, but then you get cardinality. You get cardinality from using this system in counting. So it doesn't have in itself any connection to quantity or discrete quantity, but then with the practice of counting, you get this connection of these words to discrete quantities. So here's a quote with that idea. One cannot tell what number a particular expression represents without being given the sequence of which it forms a part. And that's, I think, what I was trying to say a second ago. This says it much better. It will then be from its place in that sequence, that is, from its relation to the other members of the sequence, and from the rules governing the use of the sequence in counting, that it derives its originality, that it will derive its individuality. So, and this emphasis is in the original. He doesn't use blue, but it's italicized. So yeah, that's the general philosophical idea that is sketched at the end of what numbers cannot be, that is the philosophical background or the philosophical motivating ideas behind the system. So I see from all this 3 levels. First, there's a level of intransitive counting. It's the base level. And then you get transitive counting. That's where cardinality is going to come in. And then I didn't give any quotes connected to this, but he does talk about addition and multiplication. It's pretty clear he understands them as cardinals connected to quantities. Okay, so CA, this formal theory that I'm presenting, treats each of these levels.
Sorry, can I ask a quick question?
Transitive counting, really, I guess, there's a notion of transitive counting that will then give you a way to talk about addition and multiplication. It's not going to, it's a formal system, so it's not going to count circles or chairs or anything. But the account of addition and multiplication will be based on a certain notion of transitive, a certain account of transitive counting. Okay, so this is
Clarification question. Yes, if you want to go.
Can you hear me? Hello? Can you hear me?
I can't hear you. Raphael, you have a question?
No, a moment, please.
Is in my problem. Go now.
Can you hear me now?
Yeah,
sorry.
Okay,
Why?
good.
Okay, go.
Thank you. So, John, a question. So, how does the
Mute.
yourself.
Oh, you-
No.
Marco.
Okay, but if I
No, you can mute. And
if I
still-
mute, then we
No.
do
Just
not.
your microphone, not the.
Okay, speak.
how about now?
Yes.
Okay, sorry, John. So, can you clarify what happens with the intransitive counting and transitive counting distinction when you have classifier languages, where you have different types of counting lists for depending on what type of object you're counting? So let's say that in Chinese or Japanese or many languages around the world have classifiers. So the counting list is different from, depending on what things you're counting. So what about if you recite the counting list without counting anything, but you have to decide which list to evoke? So then what is that? Intransitive, transitive, or what is it? Because the determination which one you pick is based on the type of objects you mean to count, but you're not counting anything because only reciting the list.
Yeah, I wasn't familiar with it, so it's I've learned something here. And so it sounds, the way you described it, sounds like it's in the middle. I suppose that would be a complication that what I'm doing here isn't capturing.
Okay.
Which ought to be captured, but you would have to extend what I'm doing to capture it. But just from what you just described, it seems like it would be somewhere in the middle. I mean, the number system itself, before we start using it to count, we know we're going to use it to count. So it might, you could just, from that perspective, say they're intransitive counts. But I guess this is going to be a formal theory, so there's going to be a lot of idealization going on. And I think that it gives us a way to maybe approach those more difficult cases, but I don't have an answer right now.
All right, thank you.
Is that
Thanks.
Okay. okay? So with how CA deals with intransitive counting, it's very straightforward. It's a two-sorted theory, CA. The numbers recited in transitive counts are modeled by the index sort. The sort has a constant 1, a one-place function s, which is the successor operation, which will turn out to be the successor operation, and a binary ordering relation. And these then give you a characterization of the number word formalism. So it's precisely what you get for the number word formalism CA is this. These aren't number words anyone uses. This is a formal theory. So this sequence is meant to exist one level above the number words that people actually use, to just characterize the important structure of the number word sequences that are in use. Okay, so the idea is that this structure characterized by the axioms with these primitives characterize the ideal structure that a number system of a language must but partially instantiate. So ideal and partially are there because in a first order theory, it's going to be an infinite omega sequence. And the number word systems that we use might implicitly have an infinite number, but the words give out eventually. So this is an idealization CA, obviously. I mean, you can't
I protest.
protest.
Yeah, there's no Italian here.
I'm sorry. I should have called you about that. It's close to one of those traits.
Yeah.
Also, I have these two primitives, and in most treatments, or at least in piano arithmetic, the ordering is defined in terms of successor and also addition. So these two notions are usually thought to be interdefinable, but there's a principal reason why these are going to be taken to be primitive, because they correspond to the fundamental abilities involved in transitive counting. The successor operation corresponds to the next number in the count. And if you have a facility with the number word system, you're going to know 22 is less than 144 right away without having to deal with the successor operation. So that's the justification for taking these two to be primitive and not defining one in terms of the other.
Your relation here is not, is it primitive?
It's primitive, yes. That is what I was just trying to say a second ago.
I see.
And
Sorry.
the justification for it taking a primitive, even though we usually define ordering in terms of successor operation, is just that we know right away that one number word is less than another in the sequence. Okay, so now I want to get into transitive counting. But just one more comment about this. This is like the Benassarafian core of CA. Everything then is built up from this. This is like the starting point. Now, in CA, cardinality is not going to be based on the idea of one-to-one correspondence. So I'm going to have a different story than the one Marco sketched with the strokes. And there's a cost of not using this notion. You can't generalize to infinite cardinalities. But that doesn't concern me. The target is just the notion of finite cardinality involved in everyday contexts where we count. So cardinality, I think this is a more natural way or more natural principle to explain what's going on when we count. I call it the principle of adjunction. You have a set with k elements, and then you join an object to it. The result is a set with the successor of k elements. So here's an example of it in action, just with the example that I've been using so far. So you say 1. 1 doesn't really apply here because you need a starting case, but then 2, you apply the principle of adjunction. You had a set with 1. And then when you say 2, the point of saying 2 is not to make a correspondence. The point is to register that you've counted 2 so far. You have a set of 2 counted so far. And then you say 3. When you're saying 3, you're not saying the number 3 corresponds to that lower circle there. You're saying, I've counted 3 so far. and so on. So this is how it looks, and this is how it differs from this whole one-to-one correspondence idea. And it's a very strong claim to say that this is actually what we use, or this is what underlies what we do with counting. I'm not going to defend this, but I think it's at least a plausible alternative.
But I do not see very well the difference. Because in fact, when you say that the number 3 indicated that I counted up to 3, what you are saying, it seems to me that the number 3 refers to the stage of your counting process, not to the object, but to the stage. And what is the stage? A stage is a moment in which you have considered some object and not other, and it is characterized by the last object you consider. So you do not connect the object, but you connect a stage that is characterized by the object. So I don't see the very fundamental difference here.
Well, I mean, in thinking of it in terms of stage, well, you don't even have to think in terms of stages. When you say 3, you're saying, I've looked at 3 so far. You don't need a concept of
But
stage, you don't need a concept of sets.
you needed to know what does it mean so far. And so far means that I have considered this object already, I have considered this object already, and I have considered this object already, and this is the last one that I consider. So in some sense, you connect the number 3 with the object that you have already considered, and you have to know that there is other object to consider, it is already considered. So the last object in some sense play a role, because the object that indicate where you arrived in your counting.
Yeah, it definitely plays a role. I mean,
So
I'm not
I see
denying
the
that
difference.
because part of the principle is that you have a new object being adjoined to the set.
So
So the object itself is playing a role, but it's being incorporated into a set. So that with, I won't draw on the board, but with the one-to-one correspondence picture, the concept involved, or you have one set here, the set of numbers, and the set of things you're counting, and you make correspondences. That's not the picture I'm trying to say here. I'm trying to say it's different in that as you're counting, it's cumulative, and there are stages. So the one-to-one correspondence picture doesn't have stages. You can implement it, you can supplement it with stages. I'm just saying, let's just go directly
You
to the
mean
stages.
that you make this conjunction, but in the time that you make the next conjunction, you eliminate the former conjunction. So in some sense, the only one that you have is what you have already counted from what you have already eliminated. So you have, in fact, 2 sets here, and you have not that, but you have only one, plus this already considered here, it is already considered here.
Maybe, yeah.
I don't know, it's difficult to say without. So if I understand well, let me whether I understand well. The one correspondence is this picture here. Okay?
Right,
And then for any object, you have another one.
sure.
Your is, it seems to me, this picture here. These are eliminated. And then these are still not eliminated. And this is the one that are under consideration.
So the left of the numbers though, right?
This one is already considered. When the number here, the number word here, and the object here.
Right.
Okay, so we have one considered. That the order of that is not relevant. And the fact that it was connected to that is not relevant. What is relevant is it is already been considered,
Right.
and these are already being considered.
Right.
So there is only one connection here rather than all.
Yeah, okay.
And what you say?
Yeah, I think so. Sure.
Okay.
And then one thing to emphasize is that there's an order though,
Yeah.
because with the one-to-one correspondence, you can start with 8 and give it to an object, and 4 and give it to an object. The point here is also to build in from the beginning the sequential cumulative nature of it, which you don't get from one-to-one correspondence. Okay. All right, so if you're gonna buy this story, this picture, counting transitively involves 2 operations on what you're counting. You need what I just referred to, you need a linear order of what you're counting. Some imposition of an order on it. And then, once you have the order, you apply the adjunction principle. Okay, so this is counting, but CA doesn't formalize counting because counting involves tables and chairs and cookies. The goal with CA is to, after you get intransitive counting, is to give an account of sums and products in terms of this idea of transitive counting that I just laid out. So to give you an idea of how I'm doing this, I want to consider the most famous arithmetical equation in the history of philosophy: 7 + 5 = 12. Both Plato and Kant talk about it, and so a lot of philosophers of mathematics talk about it. So one way you can understand a proof of this, or an informal argument at least for the equation, you lay out 7 things, then you lay out 5 things, and then you count the result according to the story of counting that I just described. So the beginning will be just like the process of laying out the 7 things, but then it gets a little different once you get to the second set. Okay, so this is the general idea behind the way CA is going to give you equations. To formalize this, though, you're going to need some notion corresponding to a sum as a linearly ordered set, and then give rules for transitive counting in terms of that notion. So we don't want circled. We don't want to have any particular kind of object being counted in the formalism. But so the way I'm going to get around that is just through this observation that any such count of a 7 + 5 structured quantity will have an ith thing in the first set with I between 1 and 7. And then you're going to also have an ith thing in the second set with I between 1 and 5. So you can, so what's arithmetically relevant is just that you have objects in these positions. And so you can represent it like this, just these variables with subscripts, but then the variables itself isn't really relevant, so you can just look at the ordered pairs. So we're going to call this the indexing scheme corresponding to 7 + 5. It's really just the disjoint union with ordered pairs. But I mean, that's what it is mathematically or formally, but I mean, it's supposed to correspond to a scheme where there's like kind of spaces or holes
So
for
you
the
mean
objects.
that you construct the pairs and then you count the pairs.
Yeah, so there's going to be a pairing operation.
2 operations. You make the pairs and then you can count them.
Right. Okay, so indexing schemes, there's going to be a pairing function in CA. And so, assuming you have the sequence of number words, a pairing function, and then also, this is going to be my informal definition. So there's not this is the meta, the idea of indexing schemes outside of CA. So basic indexing scheme will just be the number words. A basic indexing scheme is defined by any number word, and it is just the number words up into and including that number word. So that gives you the ground level of indexing schemes. And then these are the ways you can create new indexing schemes given from given ones. The disjoint, what is it, the direct sum? What's the term? The direct sum of 2 indexing schemes?
Ordinal sum.
Or ordinal sum.
Yeah.
And then products would just be products. Okay, so the product indexing scheme will just be the product of 2 indexing schemes will just be the product of the 2 indexing schemes. Okay, so this is how arithmetical terms will be interpreted in terms of these indexing schemes. In terms of these just structured, very simple. It's not too complicated, but it's got a set theoretic structure interpreting these arithmetical terms.
But if I make a n plus p plus q, so I have a triple.
Well, when you n plus, so say it again.
5 plus 7 plus 3.
So 5 plus 7 will be kind of what I had already, right?
So you do plus 7 plus 3. So it's not
And then plus 3. So then this all these ordered pairs will have a 1 in front of it.
Yeah.
And then the plus 3 will have 2, 1,
So
2,
you have
2, 2, 3.
My point is, do you have the triple?
Because you can iterate the pairs, yeah.
Not pair, but triples.
Well, no, you don't have triples.
No,
so you
you
can
have three sort of pairs. Yes, sorry. Three sort of pairs. You have the pair with 1, the pair with 2, and the pair with 3.
you have pairs of pairs. And pairs of pairs of pairs.
Right.
And that gives you way
He
to.
doesn't have a tripling operation.
But you don't need it because you can encode.
Represent means
Precisely.
2 plus 3 plus 5. What is this? 1, 1, 1, 2, 1, 3. 2, 1, 2, 2, 2, 3, 4, 3, 1, 3, 2. No.
Because, yeah, so you need parentheses. So 2 plus 3,
So it's not associative, your operation.
No.
It's associative in it's associative in the
Yeah, it's
result,
very-
but intrinsically the operation is not associative.
yeah, the associativity will come out about once you count it.
Yes, associative in the result, but not in the
Yeah,
operation.
yeah.
The operation itself is not associative.
Yeah, it'll encode keep the structure you have with the syntax.
Okay.
Okay, so you have these indexing schemes, you can count them. It'll be according to the story of the adjunction principle. To do that, you need certain concepts. You need to talk about initial segments of an indexing scheme. You need to be able to have the idea of a first index in an indexing scheme, and also an idea of a next index. But these are all just straightforward or order theoretic notions. The first two. And then the first one is just the set defined. If you have an index J of an indexing scheme, the initial segment is just everything up until that index J. Okay, so given all that, you can just, you can formalize the adjunction principle that I described. We'll have a function C that takes indexing schemes in their initial segments and produces number words. Okay, so here are the rules. If you have the initial index, you can get the initial segment, or with that initial index, and the count of that initial segment will just be 1. And then the second counting rule will be any indexing scheme with K, the next index after J. So the initial segment on the left is the one right before the initial segment on the right. Or I'm sorry, it's the other way around. So K is occurring after J, right after J. So the initial segment up until K is the one right after the one right up until J. So the count of the one on the left will just be 1 extra. So that's the whole idea of the stages there, formalized.
So do you support that your index are ordered?
Yeah. Yeah, that's a good point. I didn't say that earlier. It's a lexicographic order. So 1, 3 in 3 plus 2 is before 2, 1.
Of a sort of lexicographical.
Yes. Right. But yeah, I didn't mention that, so sorry. Okay, yeah, so this is how arithmetical equations are then going to be interpreted. What's right here is just what we see in elementary school arithmetic, and what's on the bottom is the interpretation. So this right here is an indexing scheme with the counting operation applied to it. All right, so this is enough to formalize, I guess, arithmetic without induction, without generality, just the atomic terms, right?
But this become without the induction is equivalent to Robinson arithmetic?
Well, Robinson arithmetic even has a little bit more because you have the predecessor, right?
I think it is weaker than Robinson, you think?
Yeah, it's just the equations. It's what is that called? PRA or something? Yeah.
PRA?
Maybe. I mean, it's just enough to give you the atomic equations of arithmetic. Right, what I've shown so far.
Are you sure that you are weaker than Robinson?
if I know with Robinson you have a predecessor. You know that any number has a predecessor. I don't think you can prove that with what I've shown so far. But it's not supposed to be anything special here. It's just the atomic statements of arithmetic. Okay, but in everything I've said so far, just in terms of on the conceptual philosophical side, I haven't said anything about something that I think is very much involved with the concept of counting, is that there is an order, so I emphasize that, but the order doesn't matter. You can choose another order and get the same count. So that's the point of these two slides here. So here's one order, one way to count everything. And well, no, the other slides I had, the arrows were supposed to be switched. Okay, so imagine the arrows switched on my slides. All right, but the point is, if you count through one order, you should get the same result. But nothing I've given you so far guarantees that. Okay, but if you add the pigeonhole principle, then you get it. Because what the pigeonhole principle does is it associates a count with a correspondence. Putting pigeons in pigeonholes is a correspondence, right? But then you have this other data, the count. So I've given a way to talk about counts, but I haven't given you a way to talk about correspondences and how they relate to counts. And the pigeonhole principle then gives that to you. So if you have pairs, in which CA does, you can represent functions as ordered pairs. So everything's supposed to be finite, so the functions will be functions between finite quantities or finite indexing schemes. And then you can express the idea of a function. And this is how you're going to say the pigeonhole principle in terms of the idea of an injection. That if you have sigma and sigma prime, which are indexing schemes, and you have a function f between them, and then also, another typo.
Yeah.
Sigma and sigma prime. Yeah. But so the
Sigma.
this should be just
less
sigma
than
without a
sigma,
prime.
yeah.
This should just be sigma, right? So if your range is less than your domain, you're not going to have an injection. Okay, you can immediately get from this the order independence of counts. The contrapositive of this, two contrapositives of this will then give you the what this says right here. If you have a bijection between two indexing schemes, the counts will be equal. And then this gives you a way, to my mind, a much better way to prove the commutativity and associativity of addition multiplication. I'll show it more precisely in a second, but the proof of commutativity of addition is just the proof that we have when we say an n by n matrix is the same as an n by n matrix. Because the observation that it's the same can be understood as a bijection. Okay, that's the second part. Now into the nitty-gritty stuff where you can tell me what I screwed up on. This is the first time showing these primitives in a slow atmosphere, so I'm very looking forward to the feedback. Or I'm hoping there's no feedback and everything's perfect, which I'm not expecting. All right, so there's two sorts. As I said already, there's the indices sort and then the sequence sort. The sequence sort are where the indexing schemes pop up. Here are the I primitives. I've shown some of them to you, and I've referred to the pairing already.
So the first feedback, you should make the constant and the predicate I a little bit graphically more different.
The which and the what?
The constant one and everything.
Yeah, I wanted to make one
And
special, but bold didn't seem good.
Because one
No, but
may
you're right.
with me.
I get it. So that's good first piece of feedback there.
It's not very deep.
No, I know, but it's something in writing up. I've been trying to write up the mathematical details over the summer, and I don't have a lot of experience in this, so I don't know what is worth saying, what details are worth talking about, what details aren't. And then I also think my notation might be really crappy. So that's actually maybe not so substantial. Anyway, one predicate I haven't mentioned yet is this n predicate, and you're going to need it to distinguish the number words from pairs of number words. There's this function that takes the number works, it gives you basic indexing schemes. And so, but those are the only things you want to get at the ground level of indexing schemes. So to be, you don't want an infinite number of indices in an indexing scheme. So the end there is to pick out the ones that you get from a finite application of the successor operation 1 from just the pairs. So this is a detail that will come out more clearly, but that's the idea of the predicate end. The S primitives are just the ways of forming products, and there's another typo. This should be oh no, it's not that. We have the plus and the times are the way they're analyzed in CA, those indexing schemes. And then there's these mixed primitives. There's a relation, membership relation. And so this function here with the little line, it's a very little one, but that's the one that lifts up an index to a basic indexing scheme. And the domain of that function should just be the normal, not the normal, but the terms that you get from finite applications of successors of 1. And then C is the counting function. Okay, so these primitives, I can give you an idea what the model is with just giving you the primitives. I'll give you the axioms in a second, but the intended model can be read from a set of its canonical terms. Very much like piano arithmetic, its intended model are just the numerals. So here's the definition of the canonical terms. The set of n terms are just what are numerals in piano arithmetic. It's just the terms closed, starting with 1 and closed under the successor operation. The set of canonical index terms is just the n terms closed under pairing. And then the canonical S terms will be on the lowest level with the canonical S terms. You have the application of the overlying function to what is a numeral in CA. And then that closed under the operations of plus and times, CA plus and times.
What M bar is the set? Which
Yeah.
one?
I'll have a picture that explains it in a second.
Okay.
So you have this is just a general picture of how the whole thing is set up. There's more I terms than what I'm having here, but I need 2 dimensions. But I just want to show now here the connection between the n terms and the S terms. So you have overbar, which then gives you the basic indexing schemes. So this is S1 is, like in a formal sense, the set of 1 and S1. S1 overbar.
Okay.
So that gives you the lowest level of the S terms, and then you close that under the CA plus and times. And so these are all the objects of CA. There's a picture of all the objects of CA. Not all of them, I guess, because there's also the pairs. So the picture would need 2 dimensions. The I terms could come out.
So, for example, then if you have S1 comma S1, how would that relate? What would be the bar of that?
Right. So I'll answer that question.
Okay.
But yeah. Okay. So here are the axioms now. But this is the picture of the intended model. These axioms give you the n terms. First 3 axioms are just for the strict linear order. The 4th and 5th axiom here tell you that the successor gives you the next one. I'm not sure, I forgot to uncapitalize it, so I decided to have successor be uncapitalized. Sorry about that. These axioms now give you the lexicographic order. So it tells you when pairs, how you compare pairs.
So identity is defined, not really.
Identity as well.
What is the identity here? This is okay. No, sorry.
Okay.
Okay.
So the one non-canonical way you can form a term is by taking the successor operation of a pair. And just so that we understand what that is, I mean, I could leave that undetermined, but just so I just added an axiom so that we know what it is. It just goes to the right, this successor. Now this is where n comes in. So the n terms at the very least will be what I described it to be already. Or what the things that satisfy the n predicate will be what the terms of, as I've described them already. You start with one and you apply the successor operation. You'll still get an n term, something that satisfies n. And then the 10th axiom positions those objects with respect to all indexes. That if you satisfy the n predicate, you're going to be either 1 or greater than 1, but also less than any pair. So once you make a pair, it's a linear order of all indices. Once you make a pair, you're above the n, the thing satisfying the n predicate. So then we don't want this overbar operation. Given this ordering, we don't want the overbar operation to give us all indices less than a pair. So that'll be an infinite set. So it would be at least everything closed under 1 by successor. This is arbitrary. I mean, you can leave this undetermined, but it's nice to have an ordering. So
I'm trying to understand axiom 10.
okay.
So if I read it as I understand it, it will be if I is a natural number, then it is either 1 or it is larger than 1. And moreover, it is less than, I don't understand,
So it's quantifying
any
any JK.
I see.
Right, it's-
Any JK.
So the N is sort of like the initial segment of the whole scheme.
of the whole scheme. And then you have all the others. Right.
Right.
Do you need an axiom that says that there is nothing before 1? Or do you already have it because
No, I don't think. I mean, yeah. Well, no, I think it's possible. In the same way that there's
maybe it's already implicit in there because you are saying that if I is a natural number, then it is going to be either 1 or larger than 1. So maybe you don't need to say.
You're gonna-
right.
If you're gonna have an index less than 1, it's going to be a funky non-standard index. That doesn't satisfy n.
I don't understand that the last one is smaller than the pair JK. So you cannot understand it.
So I'm just quantifying overall possible indices here, JK.
Yeah.
And so if you make a pair with them, you're going to be greater than a number word. So pairs, just by stipulation here, are greater than number words. It's a stipulation with this axiom. Just so that it's these indices, just it's nice to have them in a linear order.
Yeah, so essentially what you have is all the natural numbers first, and then a copy of the natural numbers, and then another copy of the natural numbers, and so on.
With the parent.
And each copy, except for the first one, is going to have a number. Is going to be the first number of the pair is telling you which copy you are, right? The J.
Yes, but this means that all
It's like
the system of
counter
natural numbers is infinite. So you
It
need
looks like the
to.
counter word.
Yeah.
to me.
Yeah, exactly, yes. It will be
So there's a lot more I want to talk about.
Yeah.
So we might talk about this. Any questions you have, I can answer. Any of us. Okay. So one of the main theorems is that this is it's a reasoning in a meta way that if you have any two distinct canonical terms that are distinct, then you're going to be able to prove these axioms are enough to be able to guarantee you that you can decide their ordering. So I mean, this partly justifies the term canonical here. And then you also should prove that any other term that you can build will be provably equal to a canonical term. And that's the whole idea of axiom 1.8. So that you can reduce applying successor to a pair to something that's canonical. Okay, so that's the index sort axioms. Here are now the sequence sort axioms. The first axiom here is extensionality. Just that the identity of sequences are determined by the things that relate to it by membership. And so here now is where the end predicate is being used. That you can, because it specifies what's going on with the overbar operation on an index. So if your index, it satisfies the end predicate, you're going to get a basic indexing scheme.
By the extensionality, you have only an implication and not a double implication.
Because the other one, if two things are equal, they're going to have the same elements. I mean, it could be back and forth, right? But if two terms are equal, by Leibniz law, they're going to satisfy the same thing, so they'll have the same elements.
We need to give a condition of identity. It's a sufficient condition for identity, but it's not a necessary condition for identity. Why you don't need a necessary condition for identity?
Yeah, if I don't think you need it, but if we do, I'm okay to add it. Okay. I don't know, what time is it?
Go. 5 o'clock.
Okay. So the whole idea in lifting up from indexes to sequences is just that you should only lift up with the n terms, or with things satisfying n. And so this axiom is part of that. And this is where n is coming involved. This axiom then tells you what to do with your question. The overbar of a pair will just be the overbar of the right element. And you just keep on applying that until you get to a natural number.
In those pairs, okay. I think there was something that I don't know if I am understanding correctly. In those pairs, the first component is going to be always an n. It's always an.
No, it could be any index.
So it could be also a pair.
Yeah.
Okay, then I wasn't understanding correctly the previous one, but thank you.
This tells you that this axiom here tells you that the sequences you form with the plus operation come out as you want them to be. This tells you that the sequences you form with the times operation. So that's a typo. That should be O plus. That should be the circle around this. And the last axiom for the S sort, which I haven't mentioned already, the separation. You can take subsets of finite sets. And you need to do that to apply the counting operation, because there's nothing, I could have added an operation for initial segments, but I think I have too many primitives already. So you can just form the initial segments you can get the initial segments via the separation. So it's a separation axiom. But it doesn't get you to infinity because you're just taking subsets of finite sets in the standard mode. Okay, so the main S theorem is that the canonical terms, which are the index supposed to represent indexing schemes, do represent indexing schemes. So you have to refer back to the informal definition I gave you earlier about indexing schemes, but so we have something external to the theory, an idea of what it means for an index to belong to an indexing scheme. And this theorem just tells you that it works out. And then you also want them to be canonical. So you want the canonical S terms to be truly canonical. So you want to prove that canonical S terms are provably distinct. And that any term is equal to a canonical term. All right, axioms for the counting function. You need these notions that I described earlier, these order theoretic notions. And these are just the axioms. And I called them counting rules earlier. So first is abbreviating what you have at the top. Next is abbreviating creating what you have at the top, but this is just the formalization of the adjunction principle.
This S colon J, this is a set.
Yeah, you get it from the separation axiom. We know that they're going to exist from separation.
I see.
And so the theorem you want to be able to prove from these axioms is just that any indexing term, I'm sorry, any term representing indexing scheme will have a count. If you apply C to it, excuse me, you'll produce a count. So that's yeah, there's just one theorem to talk about here. And here's the pigeonhole principle within CA. The abbreviations function is representing that the sequence delta is encoding a function from sigma to sigma prime. Non-empty is just saying that it's not empty. Sigma, the domain is not empty. And then the counting function, you have this inequality with the counting function. And then the consequence is just that it's not injective. You need it to be non-empty because it's an existential statement in the conclusion. And so you don't want things being produced.
What does it mean that it's not empty? You use a language of set theory. You need a
Well, there's a membership relation.
So you need a set, you have set theory as a subjacent theory here.
There's a kind of very weak set theory.
Fragment.
It's like one way to look at it, it's like a set theory with elements and with set theoretic function symbols. Okay, so there's no, you can't iterate typing. You can have sets of sets of sets.
You only have sets of indices, right?
Yeah, and then subsets of sets of indices.
And subsets.
Yeah,
Yes.
so it's very weak. So once you get this, though, you can get all these great general results. This is why I was talking about the existence of predecessors. I don't think you can prove it without something like the pigeonhole principle. But first of all, you can get the arithmetical laws, but then you can also get existence of predecessors. And then once you get existence of predecessors, you get the least element principle in basic indexing schemes. And then what if you have the least element principle, what do you get? You can get induction. Okay, so then you can get it. This is going to be piano arithmetic. Okay, so arithmetical, this is what I was referring to earlier. Once you have the pigeonhole principle, you can get that a bijection between two sequences, their counts will be equal. And so then to prove something like the commutativity of addition, you just need to produce a bijection. If you want to show that sigma plus sigma prime is equal to sigma prime plus sigma, you produce bijection between those two indexing schemes. So that would mean you take a subset of their product where all the elements have this form. So use separation to get the function. And it's what you would imagine. Like, this is all just very technical, what you would imagine a very easy proof of commutativity. If anything else, this is the whole point. Because I just hate the proofs by induction of commutativity with multiplication. So yeah, this is what I was talking about earlier. An n by n matrix is the same as an n by n matrix. The bijection is this is what, just switch I and j with ji. You just can keep on going. Yeah, so this is what you're saying earlier. This is the proof of associativity. Distributed. If you want the details, but this is how it works. I'm going to end with, or we can stop either way.
No, the existence of the predecessor. So the existence of the successor is.
Because I have S.
Sorry?
I have S.
Because S is total.
Yeah, you just cannot.
So you take for free the existence of the successor.
Absolutely. But you're not guaranteed existence of predecessors without the pigeonhole principle. And the proof is pretty involved, and then but you need existence of predecessors to get the least element principle. So assume we have an index K that satisfies N, and J belongs to the basic indexing scheme that you get from K. What we want to prove is that J has a predecessor. So here's the picture. Just that you have a list of indices up until K. J is in that list. To make the proof work, I want to consider S of K. So you apply S, you just extend this to S of K. And then you use separation to define two sets, row prime and row. Row is just the initial segment of K bar up until the successor of J. Row prime is just the initial segment right before it. And then you define this function from row to row prime. The arrows give the idea. And S of J maps to J, J maps to 1, and then everything else maps to the successor. Now, row is greater than row prime by just the axioms, right? But then that means we have a function mapping to a function of strictly smaller size. So that means it can't be injective. But then given this whole setup, there's only one possibility for what the, it'll be just something right before J. Okay. All right, good. I was having nightmares, but that one worked at least. Least element principle. It's a proof by contradiction. So let's assume we had K that satisfies N. Let's also assume that there's something in the basic indexing scheme you get from K that satisfies phi. Okay, so those are the two assumptions. And then the third is the opposite. It's the negation of the least element principle. That if you have something satisfying phi in K, then you can always find something less than it that satisfies phi. And you get a contradiction. This is the sets you define to get the contradiction. Row is the set of everything up into S of K such that there's something less than or equal to it that satisfies phi. And so if the third bullet, the third bullet assumed, the third bullet point assumed, if that's true, then you can prove that this is a function. Just taking the predecessor will be a function. And we know you can always take the predecessor from the previous result. But then what we have is a function from something to something strictly less than that, which will then mean it's not an injection, but the way you can prove independently that successor and predecessor are injective, so that you get the contradiction. And you get induction without, I mean, you get generality in arithmetic and you get the inductive principle without induction.
Why explain me that? Why we have induction without induction?
So, okay, so here's the corollary.
You prove induction, okay.
You prove induction from the least element principle. And we all know that proof. We don't need to see it.
Okay. Well, I don't know your particular proof, but
Well, yeah, but we know the. I mean, you trust me that once you get the least element principle, you
yes.
get induction. Yeah. By the way, to get these sets satisfying phi, you need separation. That's why that works. But anyway, that's it. I'm done. I got through it all.
Questions?
Conclusions.
Oh,
Yes.
no, I guess, yeah, I have some conclusions, I guess. These are the distinctive features philosophically, I think, like, so I can write philosophy papers now based on all, if this all works, you can write some philosophy papers. One is just equalities are equivalences, not identities. The doctrine since Frege is that they're identities, and that the sense reference distinction and everything like that. But I mean that it seems to me what fits better with just our normal everyday arithmetical knowledge is that they're equivalences. That you actually have objects that refer to structures of quantities. So a sum is a structured quantity. And then there's also giving an argument that counting works by this principle of adjunction. So try to attack the one-to-one correspondence idea. Also just arithmetical generality. I gave a talk where it wasn't this stuff, but it was an analysis of a proof where you could have arithmetic generality without induction is to a philosophical audience. And that I got a lot of pushback to that. People didn't seem to like that. Which in a way is good because then you can write a philosophy paper and publish it. And then the formalism. Is it really formalist or not? We can talk about that. All right, so there's my conclusions. Thank you very much.
Okay, questions. So perhaps if there is someone in the net that want to ask a question, so perhaps it's easier that we begin with them. So if someone of you wants to ask a question, please do it. If not, okay, so other question here?
Okay.
I think Raphael's gone, so you'd be the one person asking questions.
Sorry?
Raphael is gone, so Raphael, you there?
No,
I'm here. Yes, I am.
I don't know whether he has question. He did not.
Well, actually, I have one.
He's saying something that I can't hear.
Okay. Okay, go.
Yeah, actually, I want to go back to the, the observation Marco made about the distinction. Why exactly is that this has not to do with one-to-one correspondence? So the way I see it, let's say from the perspective of human cognition and human development, how kids start to learn counting, etc. One issue is what is called partition. So basically, when you have a collection of items you intend to count, then you need to have some kind of clear mechanism that will allow you to keep track of what is being counted and what hasn't. So usually in all these presentations, the elements are static. You put a row of circles, pebbles, things that are static, so the partition is very easy to do. But let's say you're counting something like, ants moving or fish in a bowl or something like that, then partition really becomes a problem, because when you think you counted something, then you don't keep track in an easy way what is being counted and what hasn't and what needs to be counted and so on and so forth. So when you see mobile items, which occur in nature all the time, then you can see that partition really is a big issue. So when you have everything static, of course, you simplify the situation, and then the partition becomes simpler, even though for kids is not obvious, because then often they recount an object that was already there. So the partitioning is a very essential step in the process of learning how to count. So that being said, it looks to me that when you do partition, or you intend to do the partition or operate towards partition, there is some kind of one-to-one implicit goal there, because you need to have things that you're already considering and things that you're not considering, and then attaching some kind of verbal item to them. So I wasn't I'm still not clear with, Marco kind of drew those things on the board, and I'm still not 100% clear why they claim that this would not require or is different from the one-to-one correspondence.
Okay, yeah, great. The way I would. There's echo.
Yeah, it's clear. The question is clear,
the
but
question
now, to avoid the echo, I have to stop you in the procedure to speak. So now John speak, and then if you need something, I can back you to speak again, okay? So,
Yeah, the way I respond to that, is that it amounts to the same thing. So these are just descriptions. But the way I would say that it is different, so that it's not one-to-one correspondence, is that the element is not a member of the number that you've counted so far. Rather than, you don't talk about it being, you get as an immediate consequence that it's distinct from everything that you've counted so far, but it's a notion of not being in what you've counted. Does that answer the question? Or if it doesn't seem to, if it seems to collapse into one-to-one correspondence, then, but the way I understand it as different is that, so say you say 3, you've counted 2 already. The way you know that you're justified in saying 3 is that 3 is distinct from the entity of the 2 things you've counted so far. But the distinctness is understood as not being a part of something, rather than being not identical. The other idea would be it's just not identical to everything in what you count. The difference there? Or that doesn't make sense? Is it not a convincing difference? You see a difference?
So one way of seeing one-to-one, of course,
very least. So if it's not convincing to you, one thing that I am talking about, so the partition remarks are very helpful in that's something that they talk about in the cognitive science literature. One-to-one correspondence in itself doesn't give you partitions. So you need this extra structure of stages to supplement the whole idea of one-to-one correspondence in the most abstract general way. So if you don't buy there's a difference between one-to-one correspondence and what I've been saying, at the very least you need to add this story about stages with the counting.
So the way I was seeing it is that
well,
way.
now I understand what I believe to have understand before. So what I have understood before is the following. Let's try to think. Suppose that you want to count the letter of the alphabet. Okay? In the one correspondence vision, you associate A with 1, B with 2, C with 3, D with 4, etc. And so you have this function that brings from a letter of the alphabet to the natural number. In your situation, you have just a function that, for example, associate age 8, and all what is needed is to say that the other letter has already been considered and another number has already been considered. So you need simply to have one association between one letter and one number and an information of what you have already considered and what you still have to consider.
Right.
All the rest is irrelevant.
Right.
The fact that the function associated 3 to C, C to 3, that is no more relevant. Anytime that you have a stage, the only information that you need is what you have considered to one side and what you have considered on the other side. Yeah. So you have already considered A, B, C, D, E, F, G, and you have already considered 1, 2, 3, 4, 5, 7. That is all what you need. That's what you mean?
Yeah, I think that's the way of putting it. And then what you were just saying was what I think Raphael was talking about, partition. Yeah, then you partition what you're counting.
Yes, but
in between what you counted already and what you have left to count.
But this is not to say something similar the fact that you make a one-to-one correspondence, but anytime that you make the correspondence, you forget what was done before. So I don't see whether it is essentially different.
Well, okay, so I don't have any. I'm at a point now where I don't have strong arguments with the essential difference. So then I could make the weaker claim, though, if you're going to have a story about the way counting works, you have to bring in the partitions and the stages, the sequential cumulative quality of it, which you don't get with just the idea of one-to-one correspondence. I didn't really prepare a really strong argument at this point, so I can't. I mean, I believe there actually is a stronger difference, but I'm not prepared.
So John, can I add something? So imagine that rather than counting, you're labeling colors. Can you hear me?
We have to perfectionate the system. Go, Rafael. Go.
Okay. Looks like this room is more complicated than the previous room you guys had for this seminar, no?
Yes, I don't know why, because we wanted to have the advantage of the two system Zoom, but in fact it is not only an advantage, it's also a disadvantage. So
Anyway, so let me bring maybe the issue in a different way. Can you hear me, or I can hear echo?
go.
Okay, so imagine that instead of counting, you're just labeling colors in a room or something. And then, you say, oh, red. And then you point or select your partition, you identify some object or texture that has that color. And then you say green over there, you say yellow over there, black, brown, and so on. Now, you could do that in any order you want, and the labels themselves don't have any order. They don't come with any structured order. They identify a particular chromatic experience you have when you perceive some surface with a certain color: yellow, blue, red, purple, and so on. With the counting list is different, because you don't just label 4 independently of 3, 2, and 1. So in that sense, that order, when you're doing the partitioning and you're doing the counting, then when you say 4 for the fourth object you're counting, there is an intrinsic relation with the previous label in the list, unlike the chromatic example. So in that sense, is that I wasn't 100% sure with this one-to-one, because in the moment when you say 4, you're already implicitly invoking the fact that when you said 1, there was an item attached to it. When you said 2, there was another item, and you said 3, there was another item, all those existing in the partition area of what has been counted. So in that sense, the label 4 is related to the previous one in a way that the label in colors is not. So
yeah, I agree. All that. And that might just be the way to put it without stressing that you don't have one-to-one correspondence. I mean, the idea with one-to-one correspondence in itself is just that you don't have those relationships of the label to the previous labels. You don't need that. That's not part of the idea. And so I'm stressing is that the way we actually count is that that's essential. That's something that's missed by just saying one correspondence. Okay, so thank you very much for asking.
Okay, my question is a very simple, a very naive one. And there are not too much actions.
Right.
So I want to say, of course, it's naive, but there is something kind of. So it's true that in a sense, when you make a piano arithmetic, you have much more actions because you have an action schema, so you have an infinity of actions.
Sure.
Here you have not action schema, if you understand why.
Well, no, there's the separation schema. So so not only do I have a lot of actions, but I also have an infinite number of actions.
So you have an infinity of action in any case. But okay. But the advantage also of piano first order is that you have only 2 primitives. Here you have a lot of primitives.
Right.
So a lot of primitives, a lot of actions, and from a certain point of view, this can be taken as a default, the advantage. What is the advantage? That you are closer to the everyday operation of counting.
Sure.
So my question is, are you the operation of counting, everyday operation of counting in the end of the story is a very, so let's say another, why you need so much things?
So much
What's the
things-
matter too much action?
Sure.
I have the impression that what the reason for which you need so much things, action and primitive, is not to mimic the operation of counting, but to root the addition and multiplication on the operation of counting.
That's a better way to put it. Yeah, sure.
So if you wanted to do only the first things, that you say, okay, I define the natural number on the base operation of counting. Now I have my object, and then now I define addition and multiplication independent of the operation of counting. So in this sense, you would need much less because you do not need the sequences, you would not need a lot of other things. But it seems to me that you want to link to the operation of counting much more than the natural number, also the operation of addition and multiplication. But is this really required? And overall, yes. Okay, no, that is always required.
So what's required for what now? Just through.
So I imagine an alternative strategy
Sure.
that I have no idea how to realize, but the idea is that, okay, I forget addition and multiplication.
Okay.
And I try to define the natural number without operation of them, simply with order, on starting on the operation of counting. So I give an account of what are the natural number and what is the order on them by basing in a way or another using your idea or similar idea on the operation of counting. Now I have my object, the natural number, with an order. So I have essentially a progression. Now I define addition and multiplication on this object in a usual way. There are a lot of ways to do that. I define in the usual way. So at this moment, the addition is not based on counting, but is defined on the natural number that I defined of counting. So of course we have lost something, but you have a very much simplified
Sure.
your system.
Right.
But you do not want to do that because for you it's essential that the operation of addition be connected to the operation of counting.
The operation of counting are cardinal notions, quantities, discrete quantities. It's to be able to get the proof of counting to the addition without having to.
Yes, but now
For instance.
now let's see another thing. So you know Frege arithmetic, okay?
Sure.
Frege arithmetic is the equivalent of piano second order arithmetic using the Young principle.
Right.
And you know that piano second order Frege arithmetic prove Frege theory. It proves you can prove the piano action within Frege arithmetic.
Sure.
When you do that, you totally disregard addition and multiplication, and also order essentially, because the second order piano action only use successor and you not use addition multiplication.
Right.
So now you know that Frege arithmetic is interpret piano, and you can prove the piano interpret arithmetic. So they be interpreted. Good. Now we are there. Now you say, okay, but now I have no addition, and I have no multiplication, and I have no order. So now I have to define order of them. So now you have two possibilities to do that. One is to say, okay, but now I have essentially something similar to piano, and I define order, multiplication, and order as I did on piano. So I had Frege, and then I got piano with Frege, and then I forget Frege, and I define addition, multiplication, order. And so you say, okay, not very good. But you could also try another thing to define addition, multiplication, and order using the Young principle. You say, okay, what does it mean that A plus B equals C? It means the number of the object C is A. So the number of this object, so A is the number of P, B is the number of Q, and C is the number of P or Q. Okay? And the same by multiplication, you make something else. And you say for order, so what does it mean that A is smaller than B, it means that there is an injection between the concept of which the number of the number of. So now you have not used Young principle. You have not used addition, multiplication, and order to give the action, but still you have defined them on the base on the Young principle.
Sure.
So my question is whether you cannot do something similar here. That is, you still maintain the idea that you want to account for addition, multiplication, and order on the basis of operations counting, but you do that in a second stage. You begin to tell what the numbers are. So you take a much smaller number of actions. So now you know what the numbers are. And now you define addition, multiplication. I don't know whether you can do it in first order. In second order, you can do, but I think that you should be able to do it because the idea is that too much action is too much primitive seem to be something that forbids us to use your formalization to understand in some sense what the numbers are. In some sense, so it seems to me that instead of so what Peano does is clarify what we are doing when we count. Here,
No, but I'm going to push back on that. I'm going to push back on that because I don't think, I think that what we do when we count is it's supported by a lot of concepts that can logically be defined in terms of one another, but are understood independently. So that was why I spent a little time talking about it, but that, I mean, a point is that you can, one point is you can define one example of something that is usually, one concept usually defined in terms of another, is that ordering is defined in terms of successor in piano arithmetic, right? And this is just a general fact of what you were talking about as well. It's just how there's all these interdefinability relations. And one logical project, it's a very, it's a project within the foundations of mathematics, very strong, and it's very interesting, is to see how you can characterize a structure with the least amount of primitives and concepts. That's not the project here. The project here is that the concepts involved in our everyday thinking have an independence, even though they're not logically independent. So for instance, successor. And this is what I was talking. So let me just bring the slide up. When I characterize the I'm not going to bring it up. So you can characterize there's the what I call the Benasserian core of the theory, which is just one, successor, successor, one. So which is it's the omega sequence, right? And then if you have second order logic, you can do everything you say, right? This is going to be a first order theory. I'm not going to do that, but also it's just that I think addition and multiplication are not understood via the root of quantifying over sets with second order logic. I think it's much more natural to understand it in terms of schemas with which we like the addition and multiplication in a theory will be kind of like abstraction of the things we count, right? And so the specific point with respect to successor and ordering, you can define ordering with successor and addition, right? But the point is to characterize in a formal theory what we're doing with the formalism of intransitive counting, which doesn't involve any cardinality yet. And facility with that formalism means you can go to the next number. That's where the successor operation comes in. But we also had, if you don't have a facility with the formalism unless you are able to see that 33 is less than 144. You can just see that right away without taking successor and to get from 33 to 144, right? So there's a theory or a story here behind what our fundamental abilities with things like intransitive counting is, and then that informs what primitives you choose. So it's a certain conceptual structure with having the ability to count intransitively. And I want to reflect that in the primitives, even though once you put it in the logical context, there's interdefinability relations you're going to get.
No, okay. I understand. And I'm not convinced, but it seems to be reasonable to think that your two projects, that is define a natural number on the basis of counting and define addition, order, and multiplication of the values of counting, the two projects are not necessarily a coincident, that you can make one and not the other. So you can begin by one, fix one, and then to begin the other. And this would give to your strategy of action much more perspicuity, possible. And perhaps I'm wrong, but the impression that you would gain in your project if you decided to start by explaining what natural numbers are, independent of order, addition, and multiplication.
Okay.
So to give an account of natural number independent of addition, multiplication, of order. And once you have this account, then you define on this object addition, multiplication, order as you want, by still referring to the operation of counting, but in a second moment.
Okay, so yeah, I think there's a philosophical difference here though too, because I don't see my project as giving a final answer as to what the numbers are. I don't see myself doing that, and I actually am skeptical that you can ever find something that is the number. So I mean, that's just not, I'm just saying that's not my project. And I think the concept we have of number is very multifaceted and heterogeneous, and I'm just bringing all certain facets together. So the concept of number that we have with intransitive counting then becomes enriched once you add cardinality and addition and multiplication. So you don't have numbers, so let me finish. You don't have numbers as something independent. You just have the numbers you have as you understand them through intransitive counting, and then you add notions of cardinality, you add notions of addition and multiplication, you get a new concept, like a more enriched concept of number.
But this is a more, I don't know whether Raphael is still there with confirm or disconfirm me. It seems to me that the kids learn to count before learning to make additions.
Yes.
So
There's nothing different. That's perfectly consistent with what I'm saying.
yes, but what it means that we could, I say we know what natural number are. My question is not substantial. Like we give an account of a number, the omega structure, I want to say. I give a characterization of the omega structure in terms of counting before beginning to explain what addition or multiplication are. This one. And this is thing that corresponds to the idea that kids begin to learn to count before learning to make a calculation. So I think take a kid of 6 years, normally is able to say 1, 2, 3, 4, 5, 6, and is also probably to connect 1, 2, 3, 4, 6 with the object on the table, so to make transitive and intransitive counting. But still, if I ask to this kid what is 3 plus 6, she does not know. So she still did not learn addition, and even less she learned multiplication, but is able to count. So it seems to me that there should be a way in your project to characterize the omega structure on the basis of counting without taking in account addition, multiplication, and order. And when you have done that, then you give multiplication, order, and addition with definitions and not with other actions. Because in this way, it seems to me that you would reduce the number of actions and also the number of primitives. But perhaps I'm wrong.
Well, so this might be doing what you're asking. I mean, you could just look at the fragment of the theory, axioms 1 through 5. I 1 through.
So you mean that the action of sort one of this action here are just the action for natural numbers, not for addition?
Well, I mean, I'm not going to commit to saying that these are the natural numbers.
No, okay.
This is an omega sequence, right?
Okay.
This is an omega sequence. You start with the 1, and then you have the successor operation, and there's an ordering. So these
Okay, so
actions.
these are the actions for the omega sequence.
Yes.
And the other is action for addition
Well,
and
I
multiplication.
mean, it's complicated because we need pairing, right? So you need to define, they're all motivated, these axioms, with the general conceptual.
I came back on the action of here you need order, so you need the omega sequence with order. So you
Yes.
need order here as a primitive.
And the reason for that, as I said, is that I think when we learn numbers, part of what it is to learn numbers, you know right away one number is less than another without having to take the successor operation. You buy that? In the back?
Yeah.
That's generally how I learn
Sure.
numbers.
So, I mean, even though there's a logical, like you can, you don't, you can, Dedekind taught us, you just need
Okay,
a successor operation to get the omega
so
sigma.
let's put the
But-
question into way. Either you are Funes, you know Funes el memorioso, el tío el tío de
Borges.
Borges.
Jorge Luis
Borges,
Borges.
Sure.
hay una novella, account of Borges that is called Funes el memorioso.
Okay, no, I'm not familiar with that.
Funes el memorioso was a guy that had a fantastic memory, and so was able to remember everything. For example, Funes will remember the shape of a cloud that he had seen one day
Sure.
25 years ago. And so this guy does not need to have our numerical system because he remembered the order that he wants. And so he invented a new numerical system where the first word was tail,
Sure.
the second word was amleto, the third word was John Mumma,
Sure, sure.
the third word was far, then he did the order.
Yeah,
So you have the impression to be a little bit as Funes el memorioso. So you have the order, simply you use 1, 2, 3, 4, use the usual one, but you have this order independently of the natural number. You have given the order of number name, the name, the number words in a good order.
yes.
Okay. But the problem is that the order that you use is a decimal order. So you arrive up to 9, up to 9 you use only one memory. You have only the convention, you know that 7 is before 8 and after 6.
Sure.
But when you go to 11, no, 11 you are then applying addition, multiplication, distribution, addition,
No,
multiplication.
no,
No, not with 11, but with 4 times
Go, okay.
20 and 10 and 9 that the French say.
Yeah.
You are applying multiplication.
No, but also when you are to 11, because in something to 11 you already, yes, or you you start to count again the same structure. So the way in which the number,
I don't think that.
why you know that 13 is before 14?
No, those are clear.
Why?
Because 13 is a word, 14 is a word, so but
Patron, is that what you're
No,
saying?
14 and 13, they are words, but they basically on
101
Okay,
and
okay.
170.
Okay, but also 14 and 13, because 14 came from 4 and 13 came from 3. So the reason for which you know that 13 came before 14, and then you know that 3 came before 4. And
Okay,
so you have,
but that's not addition,
but you have the order that
So-
is already constructed, or the compositionality.
Sure.
So this
Yeah, I mean-
succession of word is compositional. It is compositionality
Yeah.
mirror the omega structure. So it seems to me that in the sense where you have the omega structure before accounting for the omega structure. You have the omega structure in the words before accounting for the omega structure in the objects.
Can I
have-
jump in? Can I jump in with an observation?
Audience, I don't know. I thought.
Yeah, what you're talking about are getting into details of the particular number words we use, and I was abstracting from that.
Yeah.
Right? But there are a lot of things to talk about there, and I think that's a lot what Vanessa was talking about with the recursive structure. But the one thing I would say to just all of this, I don't think you need addition. I don't think you need addition to be able to, to go up to, at least in English, to 57, count up to 57, for instance.
So I want to make an observation. Can I jump in?
That formalism, even though you have this sophisticated recursive structure, the decimal system, right? But you don't need addition, I would say.
Can you
And
hear me? Can you hear me?
it's that people can count, young, very young, little people can count, children can count without doing addition.
You're saying that people?
Yes, I am. That's the radical. thing that I
That's a
have.
radical.
So, I mean, there's a very, I think you can have, that's, I think part of the point of the intransitive counting, it might not be what Vanessa was saying, but I'm extending from it is that all what the system you have with the intransitive counting is just a omega sequence, it's a linear order.
Rafael is trying to ask a question.
Rafael, we have to modify the system of microphone.
Yes.
Because it's
Find
not
a
good.
better-
Go, Rafael.
Yeah, sorry, I was trying to speak, but it looks like I wasn't heard. So I see a little bit of a tension here in the sense that on the one hand, there's an attempt to bring what is natural when counting? What do kids do? How do we count? And so on and so forth. And then on the other hand, you have the natural numbers, which is an abstract set with a, defined and characterized by an axiomatic system, piano and others. Now, if we make an empirical observation, it would be important to make a distinction that we have what we call empirically prototypical counting numbers. So the numbers that we normally use when we count. And those are 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 13, 1, 2, 3, 4, 5 to 28, 1, 2, 3, 4, 5, 1, 2, 3, 7, 1, 2, 3, 98. But we never count, let's say, up to 1,937,000,000 ever. So it looks like there is like an overlap between what we would call prototypical counting numbers, so labels that we use for counting in reality, and then the abstract notion of a natural number. And they're numbers in the set theory, let's say, axiomatically characterized natural numbers that have never been thought of, mentioned, labeled, or counting to. Because not only they're infinitely many, but there's just like out of reach of the prototypical counting. We never count those numbers. We never think of them in a separate in a separate identity form. So here the question is, beyond a certain amount, not too far, all the labels for a number are based on the writing type, which is base 10 usually. So when you want to say something like 10,935,000, yada, 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 then we are reading essentially the writing form. So that is completely different from the labeling of the prototypical counting numbers initially. So in that case, from the empirical case, we have these clouds of numbers that have very different properties from just having the successor function. Very different. So in that sense, induction doesn't apply fully in the empirical case because you cannot reach, let's say, from a monomorphemic label like 11 to something like 1,35,000,000, 28, in which what you're doing is not necessarily counting up to that, but it's just labeling, reading the label that is written on a value notation. So it seems to me that there's a little bit of a tension when we try to characterize, formally these numbers by bringing everyday intuitions, because if we really look empirically everyday intuition, then the normal characterization of piano axioms breaks down very quickly. So I see that as a tension in this program.
Yeah, so it's a very good point.
Sorry.
Thank you for the point. I'm sorry I can't talk to you as if you're here. And every time I respond, the echoes happen. Yeah. But there's also a reason we call the piano theory a theory of arithmetic. There has to be some link between this abstract formalism and numbers as we normally understand them. And the part of the point of the project is to make that, show that link a little bit more clearly. I think to explain why this abstract theory that we have with piano arithmetic actually does correspond to the numbers that we use. So that's part of the idea. But like once you idealize, as I'm idealizing here, that you go beyond the counting them, like the things that we actually count with, this structure is just so wildly far from what we actually talk about. But the point would be the part of the point here is to isolate in that cloud that you talked about, just the very heterogeneous and complex cloud, certain distinctions that aren't normally recognized because they are actually part of our everyday concepts. So one idea here is just also with the indices, there's a point of calling them indices, that I think there's a concept of number that has nothing to do with cardinality, it's just labels, it's like bus numbers. It's like the numbers of sports on the back of the people on the soccer team. And that's a concept that is captured, I would argue, in my system with indices. And then once you recognizing those distinctions in the formalism is just a new way to develop arithmetic, I think. And it also, in doing it, you learn there's new ways to ground general concept or general statements. So it's my effort to try to motivate the project, given the points you were saying, Rafa.
Yeah, I would like to ask three things. The first is, it's not a question, it's a comment. Maybe I can help to reduce your list from infinitely many to infinitely many minus one.
Okay.
I think that you have an axiom that is trichotomy. Do you really need, I think you can prove it from the other?
Okay. Maybe with the,
I think it's your third axiom.
yeah, you might be able to prove it.
I think.
You need to say linearity.
But he said linearity in another axiom, I think.
So you have no proof of independence of the action.
No, I don't.
Yeah, maybe you're right. Maybe you need to say.
Oh, that try. Fixed.
I mean, with the,
Yeah, there.
Yeah, it's a minor comment here. I3, the K should be an I. The first K should be an I, and the second.
yeah,
K
sorry, sorry,
Yeah.
sorry.
But I think you need it to get linearity.
But because then, okay, then it's only in the canonical model that you build from the.
Yeah, only in the canonical model you don't need.
You don't need it.
Yeah,
but
but-
in general you need it. Okay, good. The second is about the canonical model. You generate these terms from one and successor and pairing, and then you prove that this is a linear order with a first element property. So this is an ordinal, a particular ordinal. I would like to know which one it is.
No, I try to characterize it with respect to ordinals. It isn't an ordinal. You can come up,
But it is.
oh,
it
no,
should be,
wait,
right? Because it's a linear order with a first element
the
principle.
canonical model you're talking about.
In the model, yeah.
Yeah, the canonical model, not like generally.
No, just the
Possible
canonical model, yeah.
Yeah, I should have figured out the ordinal. I haven't.
Okay. And the third is a comment. 2 summers ago, I was trying to teach my niece how to add. And then she already knew that if you wanted to add 3 plus 4, you can have one hand with 3 fingers and the other with 4 fingers. And then she started counting 1, 2, 3, 4, 5, 6, 7. And then I was trying to tell her a different way of counting, that you want to add 3 plus 4, and then you say 3, and then you close your hand. And then you start with a new sequence, which is 4, 5, 6, 7. So this other operation would be the first number tells you which sequence of counting you should choose, and then you should use that sequence in order to count the other numbers, which is essentially different from the other, that is, you pull all the numbers out and then you count from the beginning out.
But how do you know it's 3?
So you want to add 3 plus 4, and then the first 3.
Right, yeah, you don't put the 3 out, right?
No. The first 3 tells you that you have to choose the sequence that starts with 4. So you have several sequences to count. One that starts with 1, another that starts with 2, another that starts with 3.
Right.
So this will be a different operation that might be also.
So in this case, also addition will not be commutative.
Not from definition.
No, of course, yes.
Yes. Yeah, no, yeah, because one thing will be just say 3 and then choose the sequence that starts with 4, and then 4, 5, 6, 7. The other is say 4 and then start with a sequence that starts with 5, 6, 7. Yeah. And there are different operations, because she was able to do one very well but not the other. So,
Oh, yeah?
So she was able to put all the fingers and count from the beginning, but she couldn't understand
really?
how could you start with
Just
4
start with 3, right.
or start with 4. The counting is start from 1, so she had to learn that you could also start
Okay.
from another sequence.
Right. So yeah, that's like a convention, what you were teaching her, which is a very well motivated
Yeah,
principle, but it didn't
not at the beginning, then she understood, and then I think after a while she realized that if doing with this second way of adding, you could add numbers that are larger than 5 and 5, because now you could add 6 plus 3, because you say 6 and then you know that you have to start with 7, and then you don't have to have the 6 fingers in one hand.
Right. Yeah.
But in this way, you simplify the definition of addition. But for the multiplication, I think that the situation becomes how you can apply.
Multiplication, my niece was not ready for that.
For multiplication,
I
you
never
need a
thought.
series in any case, I think. What
You
is
can use your
multiply?
hand.
3 times 7. 7 times 3. You take 7 3 times. So you say that 3 means that you count up to 7, then you take another time a second of 7, and then you take another time a second of 7, 3 times.
And you count how many times you're.
So you are 1, 2, 3, 4, 5, 7, 8, 9, 10. That is not how what he says.
Yeah.
Yeah, it's a different kind of approach. Yeah, I mean,
This is what it does essentially. For multiplication, what is multiplication for you?
it's the set or it's the sequences.
Show me what is multiplication.
So there's a typo. So this should be the symbol of my system.
Yeah.
So if you have two sequences, you can form the product, but it's just a product. It's like a set theoretic product, right? And then, but then you apply the counting operation to it because there's a lexicographic order on the elements of that set theoretic product.
That's what they say.
No, what I was just saying is for addition.
Well, it's not exactly because to get 3 plus 4, you go for the way that's set up here. You go
It's a different, yeah.
you go with the first 3, and then it's a little different. But yeah, that
But the
I don't
point
see
is
that
that
with
in your definition of addition, you need to be able to recognize a sequence of 7 numbers starting from any number. So you need to know that, I don't know, 5, 6, 7, 8, 10 is made by 5.
So in my addition, you have multiple sequences, and the
Yes,
first
but you
number
have multiple sequence,
points
you have
to
to
the
count
sequence
the
you
element
have
of
to
the
use.
sequence. In the year system, it does not need that.
No.
Because the only thing that you need is that the sequence that finish with 7.
Yeah.
So because it's an initial sequence, it does not to count the number of sequence, you have simply to finish with 7. So is your formalization require a capacity that his formalization does not require?
Yes, definitely. My formalization requires a function that tells you from one index to a sequence.
Exactly.
And he only has one sequence.
Not only, it requires also the capacity to say, I begin with 7. Now I can count 5 numbers after 7. What does it mean to count 5 numbers until 7?
Well, this you have the 5 fingers.
So, and then you numerate the number 8, the number 9, the number 10, the number 11, and the number 12. So you need a function that take 8 to 1, 9 to 2, 3 to 3, 8 to 3, etc.
You're counting objects. So
Yeah.
you have the intransitive counting.
In his idea, you do not need it because you always have initial segments. So to count up to 7 is just to finish with 7. It's not to. And so you take 1, 2, 3, and then 1, 2, 3, 4, 5, 6 another time. And so you are only initial segment. So it seems to me that formally speaking, his definition is more complicated, but conceptually speaking, that the capacity that he ascribed to the subject to do it as smaller.
So yeah, I think there's a confusion between intransitive and intransitive counting. So when you start with the sequence 7, then you transitive count 5 objects, starting with the sequence 7.
Yeah.
That start at 7. So there is no you don't have to do any transformation into the 7 into 1 and the 8 into 2.
Okay, you are. Let's say in your formulation, you mixed transitive and intransitive count.
But this is
No, not really.
Yeah, he's also doing that, no?
Not
I mean,
really.
you have your intransitive counting, which are the numbers one successor of one successor.
Yes, then they count pairs.
And then
they
you
count the
count
pairs.
you count things.
Okay, that's also where you count the pairs. But you still count, yes, starting from the initial. Okay. Okay, other questions? So if there are no other questions, we go to beer and then to dinner. Thank you.
Thank you.
Thank you.
Investigation.